Good evening, everyone. We are continuing with our course Geomorphic Processes, Landforms and Landscape, and this is the weekly live session. So, we are in on the fifth week of this course, and so last week we had started with understanding the basics and also the some of the examples of fluvial geomorphic landscapes and landforms. So, fluvial geomorphology is the study of how landforms and landscapes are developed due to the action of moving surface water. The most common example of it is the rivers. So, we had learnt about the different morphological terms that are associated with a river, and also the stages the river undergoes through during its course, from the point of its origin to the mouth of the river where it meets the sea. And we also try to see at which stage of the river what kind of landforms or landscape development happens. So, since fluvial geomorphic processes are actually found much in abundance due to the presence of river drainage basins very vastly spread out all over the world. So, it is important for us to understand uh, uh, this portion of geomorphic processes. So, we saw how at different reaches of the river or at different stages of river, uh, either you will have more of erosion or more of deposition that is happening. So, we also learnt a little bit about the different kind of channels that can be forming at different stages of the river's life. So, building on that, we will move today towards understanding what are the stages of the river cycles, or during the life of the rivers, what are the different stages that occur, uh, which actually changes the different landforms, which changes the landscape around the area through which the river is flowing. So, as we had glimpsed through in the last week, the different kind of uh, structures, landforms, landscapes that are formed at different stages of the river's life. So, when it is in the young stage, mostly we get V-shaped valleys, gorges. These are mostly landforms that are formed due to the erosional function of the river when they are flowing at at steeper sloping areas. Mostly these are formed around the areas where the rivers are originating. So, because they usually occur or they usually originate at high altitude places, so the slopes are very steep, and because of that, the velocity of the water that is flowing down is also high compared to when you have gentler sloping areas. So, because of there are many other factors also which actually play a role into in understanding what kind of landform would be formed owing to the natural agent acting over there. But for the younger stage, most of the landforms that are developed is usually due to erosion. So, mostly you can see it is also called headward erosion. So, head is the downstream part of the river. The head is the point of the river which is moving downwards, moving onwards. So, uh, usually they are narrow V-shaped valleys, gorges, and also at places uh, the development of waterfall happens where there's a sudden change in the elevation and the water drops down due to that. So these are all the kind of landforms that are formed in the younger stage of the river. When we come to the mature stage, so in the mature stage you will have combination of both erosional landforms that are forming as well as some depositional landforms that are forming. We had discussed some of these examples in the last weekly session. So mostly I think what you can see, the significant feature that is formed during the mature stage are the different kinds of drainage basins. So based on that, the kind of channels that are going to form, the uh, uh, the the amount of area that would be covered by the river systems also depends on that. So you have well integrated system. So mostly this relates to the drainage systems that are formed. You have meandering channels. So meandering channels are where the rivers form they follow a sinuous path. So usually they start as straight channels, and due to the changes in the slope of the area as well as the amount of sediment load that the river water is carrying and the velocity with which the river would be flowing, different kind of channel patterns develop, and usually these develop in the mature stage of the river. So meandering river channels are very much signature of the mature stage of the river systems, and cutoff channels are actually due to uh, an equilibrium balance between the erosion and the depositional work done by the river. Some of these meandering channels can actually get cut off from the main channel, and the channel might then suddenly start flowing in a straight channel. Then again after a while it can again form a sinuous pattern. So the dynamics of the erosion and the deposition in the mature stage of the river is usually changing with time. And some other there are certain kind of valleys that do form even in the mature stage, but mostly they are asymmetrical or broader valleys. So for the younger stages, mostly you will find narrow V-shaped valleys. Okay, so narrow V-shaped valleys, or you will have some sort of a little slightly U-shaped valleys at the um, at the lower parts of the areas where these river systems are actually forming the landforms. But in the mature stage, most of the valleys are usually broader at the base, and they might be either asymmetrical like this is asymmetrical, or you can have symmetrical broad valleys that are formed. These are symmetrical, and the other these are the erosional landforms that are present during the mature stage of the river system or the river's life. The depositional landforms that are usually found in the stages are the floodplains, natural levees, uh, we have river terraces that form, and meander scars are also the meander scars is where we were explaining that this channel might get cut off from the main channel, and it might form an oxbow lake in the start. And if the water gets evaporated, then this kind of the uh, impression that is left behind, it appears like a scar and meander scars. And if many of these scars occur in groups over here because of the changing direction of the movement of the meandering channel. So it can start from this side. Okay, so when you see meandering scars, suppose to the right side of the current channel, so you can understand that the river, the way that the river has changed its course, at least in the lateral sense is from the right to the left hand side. So then you have point bars, which are important. So point bars are usually depositions which start at the you know which start at the inner corners of the meanders. So these first start for depositing, the river starts depositing the sediment load in the inner corners of the meanders. And when these suppose with time the meanders are coming closer to each other, so what happens is these sediments that have been deposited here and the sediments that have been deposited here, they will merge and then they form something of this sort. Okay, and the water kind of moves around it. So these are actually called point bars. So these are usually made up of sediments. And then you have back swamp deposits. So as we said that the oxbow lakes, so sometimes they are very larger in size and then they support their own ecosystem, and with time the stagnant water that is present over there, it can turn that area into a swamp kind of landform. So with this, uh, why they are saying that the number of tributaries reduce in the mature stage is because most of the channels which are present at the younger stages are very narrow in nature. And since the river, the origin of the river and the main channel of the river is supplied by water from different such narrow and smaller river systems, so the tributaries as we say. So when they are descending from the elevated areas where they are originating, they at the foothills, or at areas which are lower than the foothills also. So that's where they join the main river channel. And since most of the tributaries are then actually joining the main river channel, hence the number of tributaries reduce when the river is moving onwards from the younger stage to the more mature stage of its life. What happens at the older stage now, since the number of tributaries are already reducing at the mature stage, at the old stage the tributaries very are far fewer in number. And mostly the river itself starts forming new lower order stream channels, because more deposition keeps happening, because at the older stage a lot of finer sediment load is actually brought down to the areas where the river would be meeting the sea or ocean. So because of the high sediment load, and then that getting deposited, so and the water itself has very low rate of flow at the older stage of its life. So there are no more incoming channels or incoming tributaries which are giving more water to the channel. So the dominant process that would be that you can see at the older stage is actually the the deposition of the sediment load that the water is carrying. So you can have, like, if we only consider the types of if any few erosional landforms, if any are forming, it would be extremely broad valleys with gentle slopes. So these can mostly occur if there is a change in the slope of the area or the elevation of that area. Uh, Otherwise, it is very difficult for the river at its older stage to erode a very highly resistant substrate, or form newer valleys or erosional landforms at the old stage. So in the figure on the right, this figure, so these actually give the different stages that we kind of looked through when I was describing it. So you have the early youthful stage, and then you have mostly falls and some areas where the water gets it gets accumulated, and larger depressions maybe, and lakes could be forming. Then you have the youthful stage, then early maturity and the older stage. So you can see that in the start, mostly the pattern, the way the river is flowing is straight in nature, okay, almost straight in nature, and their width is very less. Width, as in the channel width that is there, is very less, and you can see there are more number of such narrow channels actually meeting the main river channel, and then they are moving downwards. When the mature stage is starting to form, you can see that there are few tributaries still present over here, which are supplying the water to the main channel, and the main channel starts to flow in a sinuous channel pattern. Then at the mature stage, okay, it's you can see that it's mostly meandering in nature, and you can see that one part of this meander is cut off from here and forming the oxbow lake, and as when after it is cut off from the main channel, so the channel itself starts flowing in a straighter manner compared to its previous reach, where you had mostly sinuous channels that are there. And over here you can see there are still some tributaries which are flowing into the main channel, but the number over here and the number of tributaries over here is different. And then at the maturity stage, you can see that the basin, okay, through which, or the area through which the river is actually flowing, becomes much broader, okay, compared to where the area that it was flowing over here in the early matured stage. So with that we can understand that with increase in the time, the basin area, okay, the basin area, or the area through which the river is actually flowing, it laterally becomes wider, and the depth also, I think mostly it is uh, the depth as a function, it will increase in the older at the older stage. So it can be that is why when uh, at the if the depth does not increase, so it cannot accommodate the amount of discharge that is, the amount of water that is being brought down by the river from the youth stage to the through the mature stage, and all the water that is being supplied by the tributaries. So the depth increases as well as the channel width increases, from the youth stage to the older stage to accommodate for uh, the amount of water that is flowing as well as the increasing sediment load that is brought. So if we try to see how the discharge varies with respect to different, as you can see, the different factors that uh, govern the amount of discharge. So if we see Q as the discharge, okay, and if we consider the width of the channel, of the river channel, so we can, it is seen that at say younger stage, and then you have the mature stage, and then you have the older stage. Okay, so if you take a cross section along, at any at these stages of the river, we can see that the width of the channel increases when we move from the younger stage to the older stage, and the amount of discharge also increases. If we consider the depth, if we consider depth versus the discharge for the younger, mature and the older stages, we can see it follows a similar trend as the width, and you can see that with increasing in discharge, the depth has to increase from the younger stage to the older stage. And now if we consider the velocity of the of the flow of the water in the river, so you can see that the velocity change is not very significant. Just yes, so the velocity change isn't very significant, but there is certain change to accommodate for the increasing in discharge. So as the discharge increases when we go downstream, uh, the width of the channel, okay, and the depth of the channel, and as well as the velocity with which the water is flowing in the channel have to increase. So that is why it is possible for larger channels and deeper channels to be formed even at the older stage. But the lateral erosional processes, or the rate at which the lateral deformation can place due to the flowing river actually changes from the younger stage to the older stage. It becomes higher when we go to the older stage. So you can see over here, so if we consider this as like the river valley or the river basin, you can see that laterally it has a much higher cross sectional area. So the normal cycle of erosion, what is understood by that is the cycle of erosion by the running water, because you know the normal cycle of erosion can be mostly associated with the erosion that is carried out by the running water or river. As I said before, that the most abundant geomorphic landforms that are found on the surface of the earth belong to fluvial, the fluvial category, because the river systems are widespread. Every continent has numerous river systems, and they also cover a large area. The river systems flow through major parts of the land on earth. So that is why the normal cycle of erosion is usually associated with the fluvial erosion that we see. And because it is one of the most important and widespread geomorphic agent, understanding the cycle of erosion that takes place due to fluvial agents, that is river, is necessary. So at the start, uh, what causes the erosion? So just water flowing across the land is not just going to help in the erosion of the land. So there has to be some other force or some other process also which aids in the beginning of this erosion. So the uplift, okay, so suppose this is a surface across which the river would be flowing. So if the river is flowing on this surface, there is not there is no slope difference. So because if there is no slope difference, there is no change in the rate of flow of the river, or the sediment that is there might not be or the rate of the flow of the water itself is not going to be enough for it to carry the sediments that is contained in the water. So for erosion to at least start, there needs to be some change in the topography of that region. So if there is an uplift over here, okay, so there is an uplift over here, suppose. So now the surface water that is flowing, there is going to be a slope difference, and that is going to help in the increase in the rate of flow or the change in rate of flow, and because of that the water will have more power to erode this substrate as well as carry whatever sediments is being eroded from here and carry it forward downstream. So the uplift of any landmass with respect to the mean sea level is necessary for rivers to even originate and flow downwards, and that is when the erosional work starts. So the rate of uplift in the beginning, okay, so where the rivers are originating over, so suppose this area is the glacier, okay, most of the rivers as we know originate in glacial areas. So over here, if this remains as a lake, okay, so there is no uplift happening, or there is no change in the terrain. So the when glacier melts, the water over here will stay in this area only. It will not move downwards. It will not help in originating the river. So but if this area gets uplifted, okay, so that is when the water can move downwards, okay, move downstream, and then it can start the process of the fluvial geomorphology as what we are seeing. So hence in the beginning the rate of the uplift has to be more than the rate of erosion. If the rate of erosion is higher than the uplift, then the uplift is the uh, mm, the surface which is uplifted will get eroded much faster, and that change in the elevation, change in the topography will not be achieved for the water again to flow downstream. So hence the rate at which the uplift and the erosion has to happen has to be different, with the rate of uplift being higher than the rate of erosion. So with the progressive development of the river geomorphic landforms, so like the valleys, and then later on the stages for it to start. So the as you can see over here, okay, this is where the rivers are originating. Now you can see that there are differences in the terrains, okay, so there is uplift, and then they will start flowing through the areas, okay, so these are when the valleys are slowly they are starting to form over here, and then the water is actually trying to flow through the valleys between say two elevated regions. Okay, so this is where you have your valleys forming and the river is starting to turn into the mature stage, and then slowly it will reach its mature stage and it will try to branch out and reach try to increase its reach and the drainage basin area. And then lastly you will have the older stage where you have mostly what we call the peniplanation. So peniplanation is they try to um, they try to convert more and more area in a plain kind of a topography. Okay, so not valleys, not kind of any high elevated areas. They try to make the area more plain in nature. So this meandering that is happening, this starts to spread laterally, and the erosion work is still going on, but the rate of it is still low, and also there is no uplift over here. So there could be the rate of erosion might be higher than the rate of any uplift happening in the mature and the old stage. So when that happens, so there can be more lateral expansion of the landscape that is formed due to the river. So one example where we can see this uh, the understanding of how uplift can change the way the river is actually flowing, and also the kind of landforms that can be formed is the formation of river terraces. So as you can see, these are step like features that we see over here, and the river is flowing through the in from the middle section, and these are actually flanking it on the sides. So they extend along the side of the valley, and each of the terraces actually denote their past uh, the past elevation level of the river valley. Okay, so if you see, consider T1. So when you try to if you imagine that the surface was at this level in the start when the river was forming. So the river would be flowing at this elevation compared to your mean sea level. Okay, with time the channel, as we said, the lateral expansion starts occurring at at an increasing rate than compared to the uplift of that area. So if there is no more upliftment happening over there, so the river itself does all the erosive work, and it will start broadening the river valley. Now maybe uh, you know uh, either with erosion, the the river terrace is already formed, but maybe there is a sudden shift in the, or there is a sudden uplift in the area beyond the river, or there could be a kind of subsidence that has happened in the downstream part of the river. So what happens is the channel slope has changed, and that could again mean that this end of the T1 and the start of the T2 can signify a change in the elevation of the area through which the channel is actually flowing through now. So these different occurrences of terraces can help us in understanding the uplift, the history of upliftment in that area also. Any orogenic occurrences that might have taken place in that area can also be studied by understanding these river terraces. So you can see that this is the modern floodplain. Okay, and these are terrace surfaces. These were also the flood plains when the river was flowing at that at that level compared to the the main sea level at that point of time. So you can see that the upper part is the river deposits, and this is the hard rock which was there previously, but now it has been eroded away. So when these deposits were forming, actually these deposits have also formed due to the um, deposition of these sediments that were initially formed by these that have been sourced. Actually the source would be this bedrock over here. So there are two types of terraces we can see, that is erosional terrace and depositional terraces. So erosional terraces usually form where uh, the material that is existing on the sides of the river channel or below the river channel is essentially a very a weathering resistant rock. Okay, so they are also called strath terraces at times. So mostly it is made up of bedrocks. You can see over here these are bedrocks, so there is not much erosion in the terms where these rocks have not been easily fragmented and turned into sediments. Some sediments are there, but mostly these sediments are deposited on the bedrock terraces. Okay, and the next one is a depositional terrace. So these are usually formed when the river is flowing through unconsolidated sediment areas. So mostly these could be alluvium which are deposited on top of a bedrock, but the river is not cutting through the bedrock, but it is cutting through the softer or the not consolidated sediments that are present over here. So they are also called valley fill deposits. So that's why we saw river terrace. So this is your terrace one. So in the beginning maybe the river was flowing at this elevation level. Okay, and then with time when erosion must have taken place and the development of the floodplains had happened, and maybe due to a change in the slopes due to uplift either in the upstream or the downstream region, second terrace formed. Okay, so there was a drop in the elevation due to erosion or uplift and then another terrace is formed. This was where the floodplain had formed when the river was flowing at the terrace 2 level. Then after a certain time again there would be work of erosion as well as uplift, and because of that the third terrace is formed. And now at present the river is forming the fourth terrace. Okay, but with time when there will be again a sudden or a drop in elevation and the river starts flowing through the bedrock over here, so that is when your fourth terrace would form. So we understood how with time the river can form wider and deeper valleys as well as the river terraces on the sides of the channels. Now we will come to another aspect which is called the river rejuvenation, where the rate at which the erosion is happening can change. Okay, and when it is saying that it is being rejuvenated, as in its uh, uh, what it its capacity to erode more increases. Okay, when we say the river rejuvenation is happening, so it can erode more, and this can be due to changes in elevation again, uplift, or there is a subsidence that is happening. So river is rejuvenated when its base level is lowered. So rejuvenated as it has got now more energy, or in layman terms it has got more energy to erode more. So you can see over here that at this region the river is entering into a sea. Okay, as we said that the erosive power, or vertical erosive power of the river at the older stage is low. It can erode, significantly in the lateral manner, but vertical manner it is low. So what we can see is that if the sea level falls, okay, so if the sea level falls, there is sudden elevation difference and more area is exposed, and because the water now has to accommodate through this changed slope, it will start eroding more. The channel slope over here has increased, so the river will cut into the floodplain and it will start creating a new smaller floodplain nearer to the mouth of the river. And this area where the river is intersecting the area where the channel slope has has increased is where you can find waterfalls. And what happens is, because this area is getting eroded very faster than compared to this area again, so what happens is this keeps shifting back. So the point where the channel slope is increasing and more erosion is happening, it keeps shifting back. So you can see over here that the river keeps cutting back and the waterfall then turns into rapids further back. So you can, this is a kind of a plain view of how river rejuvenation can happen. If you see the cross sectional area, so at first this was the channel kind of a slope that was present because the original sea level was over here. So if the fall in sea level happens, okay, so you can see that the slope was like this, now the slope has changed. So so the water is going to bring more and more bigger size sediments over here, and it can deposit over here. And then if the sea level falls further down, and now you can see if this is the present sea level, you can see how the slope has changed again compared to what it was over here. So then what happens is that it reaches the mouth of the river. So these nick points are where you can have your waterfall or your rapids. So these there are some other kind of changes that are associated with the river rejuvenation and the different stages of the river, is that you have the isostatic change, eustatic change, nick points, and incised meander. So isostatic change is that when the land also moves up and down relative to the sea level changes that is happening. So mostly these are due to the endogenic processes that we have seen before, crustal movements or plate tectonic movements. Then you have the eustatic change, so that is due to the rise and fall of the sea level as an action of the or as a consequence of the glaciers melting, either lower in melting or causing a shrinkage of the glaciers, or rise in the sea level due to more melting of the glaciers. Then you have the nick point, as I said that it is the point where the there is a sharp change in the slope gradient in the river channel itself, and this is usually due to the at the areas where the sea level drops. Okay, so from the previous sea level, okay, so that point where the slope is changing, that would be your nick point. And incised meander is actually when the river is down cutting, um, mm, suppose this is your land, okay, and the river is flowing, so maybe not so plain, but slight slope, and the river is flowing, and it is meandering also. But due to sudden uplift in this region, okay, so the slope changes suddenly, and what happens is the river will start down cutting this area at a much higher rate than it was cutting at this area in this region. Okay, so that is when your incised meander. So you can see over here, these could be called your incised meander. So now we saw how the different how the cycle of the normal cycle of the erosion, as we say, or the at what point this cycle of erosion can be reverted, or it can be kind of aggravated with the change in the slope of the region, by either uplift or the fall in the sea level. So now we come to channel patterns. So channel patterns, as you can see in these kind of 6 terms, these are the factors that help in forming a certain kind of channel pattern. So if you vary any of these factors, your channel pattern would change from the pattern number. So these numbers actually, this is a classification that was given by Shum. So you can have a channel pattern 1, 2, 3A, 3B, 4, 5. Okay, so you can see that actually the most basic channel pattern which we start with is the straight kind of a channel, and then slowly with time, okay, as the erosion increases and the sediment is carried by the river, so it will start depositing at certain place. So you can see how the river tries to follow a sinuous path, but the channel itself, the cross section, does not become meandering yet or sinuous in nature yet. It is still straight, but with time, because these sediments can start for increasing in size as well as depth. So what happens is the water tries to flow around such deposit, and then you can have channels which form the 3A, then 3B, then 4 and 5. 5 is usually seen in kind of the mature stage, later mature stages also, where mostly the channel, the river banks would appear straight, but the water is actually trying to flow around different mounds of sediments that have been deposited. Okay, so over here with more suspended load, okay, so there is not much load that is being dragged by the river along its bed. So there is mostly suspended load. So the velocity, or the way that it is going to flow is going to be straight, since it is not kind of depositing, and it is not being resisted much, uh, in a more than the other areas that we see over here. So you can see that relative stability is higher for channels which have suspended load compared to when they have bed load, and sediment sizes of the of the channel type that is governed by sediment load is also smaller than bed load channel types. Then again, varying the sediment load is much higher in the channels which are which come under the bed load pattern. Then the flow velocity also differs, then stream power also differs, and this is if we see it in the horizontal manner, we can classify them as per on the terms of the load that are carrying. But if we want to see whether how the channel pattern varies as per the shape that it is, or it is going to flow with, is that for the straight ones you will have, the straight channels would occur in areas which have low gradient, and the width per depth ratio is also low. So the width of the channels need to be smaller than the depth when we are considering straighter channels. But in higher width to depth ratio we find more braided channels, and meanders actually form the kind of the moderate values of all the different factors that we have. So over here you can how the sediments that are carried by the channels, how they would be getting deposited. So the bar that is present over here, suppose this was a bar that has been deposited in straight channel, what happens is that slowly, if the with time this bar might get shifted downstream, then you can have either part of this bar stay remains here, and some part of it is dragged ahead and then forms a different bar. So this alternate bar shift can also happen. Then neck cutoff, as we had also discussed, with increasing in deposits, or kind of changes in the rate of the flow of the river, also this neck of the meander can get cut off, and then it can again start flowing in this in straight pattern. So similarly you can see these are kind of the different variations in the channel patterns that can be observed. So you can have a meander shift, so maybe due to different say crustal uplift, or subsidence that might have happened either in the upstream area or the downstream area, and the meander shifts, and then either the convexity of the meander curve either increases or decreases. Then you have avulsion. Avulsion can happen when the channel kind of abandons its main channel, and it starts flowing in a different direction. This can also happen when you have certain kind of tectonic it can happen as a consequence to any tectonic movements that might have taken place in that region. So now we come to the drainage basin or watershed. We had gone through few of the things already, but this is we'll try to see more factors which which control the kind of drainage basin that are present, and also the amount of discharge that can that uh, is flowing through the drainage basin due to the the river that is flowing through the basin. So some terminologies that we have to remember: obviously the drainage basin, that is the area of the land that is drained by the river. Catchment area is the area within the drainage basin, so where the water is there. Then the watershed is the kind of the boundary of the drainage basin, which separates one drainage basin to from the other drainage basin. Then obviously you have the source, though that is the beginning, the origin of the river. Confluences, where two rivers or streams join, and then you have the tributary, that is smaller stream or river which joins the main channel or main river, that is that is actually the part or the main part of the drainage basin. And mouth is obviously the point where the river meets the where it is entering the sea, so it is the end of the river for that matter. So we had seen how the drainage evolution happens. So in the youth part, there are suppose this is the origin or that we see. So sorry, this it would be as we had seen before that the most of the water is actually coming in, and the channel width is very narrow, and so these don't reach out to very to larger areas. It's mostly focused on going from the upstream area to the downstream area in the youth stage. So as and when the stages start moving from a younger stage to the older stage, more and more lateral expansion of the drainage basin can occur due to the flowing river. So the drainage morphometry actually helps us in understanding which is a densely populated drainage basin and which is not. So for example, if we the term we had looked at this in the previous slides, in the previous week's slides, that bifurcation ratio. So it will help you in understanding the branching pattern of the stream network, and it can also give you an understanding of the drainage density. So usually it has to be more than one. So we can, if we try to calculate over here, okay. So suppose we are trying to understand the bifurcation number of one particular order, okay. So say 1. So over here you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have 9 first order streams. Okay, actually the largest channel would have higher stream order number compared to the smaller ones. So that actually are seen at the edges of the drainage basin, and we divide it by the number of streams of the higher order of it. So you have 3 second order streams. So this is actually the bifurcation number is 3. Now, if we consider this, this drainage basin, if we count all the streams that are representing the first order of streams, so 1, 2, 3, 4, 5, 6, 7. So you have around 46 first order streams, okay. So first order, and then if you divide it by the second order, so second order you have so that's 20, okay. So that would be around 2.3, okay. So you can see that the bifurcation ratio of the first order streams with respect to the second order streams for this drainage basin and this drainage basin is different. This is much higher and this is lower, okay. So this can also uh, help us understand the drainage density. So drainage density would be the ratio between the total length of the streams in the basin and the drainage basin area. So if you measure the stream lengths of each and every stream order and you divide by the area of this drainage basin, you can understand the drainage density. So the drainage density, if it is higher, okay, so the amount of water that is being discharged by the main channel and to the stream orders of lower numbers, the it has more capacity to hold that discharge. Okay, so the flooding, the the it is less prone to flood compared to when you have drainage patterns like this. Okay, so over here, if there is the if the discharge increases in this drainage basin, so as we see that the lower stream numbers or the lower order streams are much lesser in number, so the water cannot be held by these streams and it will flood the drainage basin itself. Okay, so there is the capacity for such a drainage basin to hold change or increase in discharge is much lower compared to a drainage basin which looks like this. Okay, so this is how this is kind of a quantitative way to understand how drainage basins will react to changes in the amount of discharge that can happen by sudden flooding factors. So one important aspect of how fluvial agents actually can change the landscape of an area is also river piracy. Okay, so river piracy can happen is uh, one river can actually uh, kind of steal one of the streams that is flowing into another river and start making it supply the water to itself. Okay, and the river from which from which the channel has been stolen would suddenly change the way it is flowing. The discharge, the amount of discharge decreases, and maybe if it was a main river channel which was actually supplying the water to it, it can start drying up with time. Okay, so you can see that one of the way that it can happen, it is called elbow of capture, where this river starts headward erosion. Okay, and this is the watershed divide. It kind of intersects with the watershed divide of this river which is flowing in this direction. Now this river is flowing in this direction, and this river was starts eroding in this side. Maybe there was an uplift in this region, okay, which causes the river to kind of slightly change its direction of flow, and the erosion by this the headward erosion is much higher than the much higher compared to the erosion that is happening over here. So what happens is this river will capture this river. Okay, now since this river was already flowing in this direction and it has been captured by this new river A, so the river B now starts flowing into the river A. So this area, so this becomes the abandoned channel. Okay, so now this river stops receiving both discharge and sediment load from river B. So this is called the river piracy. So the basin area that was actually part of this river, okay, has been captured by the drainage basin of the river A. So this is called river piracy, and this actually affects the both geological aspect of that region as well as the anthropogenic consequences are also present. So it maybe what happens is that the slowly this river might not receive enough supply of water, and this will start probably start drying up, and it won't be able to recharge the groundwater of that region anymore, and it would lead to more uh, drier environment in that region. So river piracy is profitable for one drainage system, but it can be very negative. It can negatively impact the other drainage basin. So uh, so the river piracy, as well as what we had discussed before about the different kind of morphometric analysis of drainage basins, actually help us in understanding kind of different drainage patterns that can be formed with time, and drainage patterns itself are a part of the yeah. So drainage patterns rely on both the different kind of balance that is present between uplift and the erosion that is done by the river, and as well as the underlying geological strata that is present in that area. So you can have concordant drainage and discordant. We had discussed this in brief manner. So in concordant drainage, that the pattern, okay, so the drainage pattern follows the kind of trends and the features and the structure of the underlying area of that region. But for discordant, what we see is that the river flows in its own way and it does not follow the prevalent trend that is that we can see at that point of time. Okay, so and then you have another type of drainage, that is superimposed drainage. So there could be a drainage pattern which was present in the past, but a new drainage pattern has now formed over the older drainage basin. Okay, so maybe the older drainage basin was changed by erosion, or as we know that, as we saw even that river piracy could have taken place, and suddenly the drainage the drainage pattern has has modified into a newer drainage pattern. So you can see over here that this is how the this is consequent. Okay, so this is how the drainage the how the river is flowing, and maybe with time antecedent, you can see over here that due to uplift, okay, we can see an uplift over here, but there not much has changed in the way that the river is flowing. Okay, so this would be a kind of kind of a concordant drainage. And then superimposed, this can be seen that this uplift you can kind of see over here. I'm not sure how clear it is. Okay, so this you can see the uplift is present, okay, and the drainage pattern is there, okay, but the drainage, the it is superimposed on the kind of this tectonic the tectonic setup that is present over here. Okay, so consequent drainage patterns can lead into both superimposed and antecedent drainage patterns. Now over here, this is kind of an observation of how different kind of drainage patterns can occur together. So this is the consequent river stream that is going. So these are the direct consequence of the initial topography. Okay, subsequent is that these will develop after the master consequent. So consequent streams are developed, subsequent streams are developed on the basis of the consequent streams. Obsequent streams are which have a direction opposite to the consequent one, and resequent one are they will flow in the same direction as the initial consequent stream, but they are formed due to difference in the relief that is happening in that region. Okay, so you can see over here, so this is a consequent stream and these are the subsequent stream. So this is flowing in this direction. The subsequent stream itself is trying to follow the master consequent streams direction. The obsequent river over here you can see is following the opposite flow direction of the consequent one. So and the resequent one is flowing again in the direction of the consequent stream over here too. Okay, and now we see a better kind of diagram which can explain the superimposed stream. So the before the stream was present, okay, the deformation might have occurred, and the dendritic streams are or this is kind of horizontal beds that are present over here, and this is the initial pattern, drainage pattern that is there. Now with time, the erosion has taken place, and this drainage pattern is still present over here. Okay, but due to maybe now with erosion you can see that this kind of folded structure is exposed over here, and uh, because of that there is a change in the rate of erosion that can be seen over here. Okay, so the horizontal beds are stripped away by erosion, and the drainage pattern is now superimposed on the new kind of tectonic setup that is present over there. Now, we had kind of looked through some of the very common drainage patterns even in the last lecture. So, in this few slides we will see more varieties of drainage patterns that are present, and also see the different kind of live examples. I have some pictures of different drainage patterns, how they look in real life across the globe. So first we have the dendritic. So these are usually irregular, branch, tree branch shaped streams are formed, and they usually flow over the area which have the homogeneous substance that is there. So there is not like a mixture of different kind of sediments or rock types are not present. So uh, usually they try to flow through the different fracture zones that are formed due to weathering and erosion activities of the fluvial agent, and mostly they form in regions which do not have very steep slopes, so gently sloping areas. So usually you will find dendritic drainage pattern over there. Then you have parallel ones. So these usually occur when in the elevated areas, when the rivers are flowing from their origin downwards, okay, along the steep slopes, and mostly they are the streams are parallel to each other, and these can be also found on the sides of fold mountains, because between the two folds you have elongated valley kind of region, and because of maybe consequently parallelly folded mountain sides, you will have uh, parallelly flowing streams. Then you have trellis. So these are usually found in again these can also be found in folded areas where you have number of, say, you know the axis of the mountain is here and these are the slopes. Okay, so these are parallelly folded mountains maybe, and these areas are the valleys between the two fold mountains. Or you have um, kind of joints that are formed also in that area, or maybe zones of weaknesses which can also form. Then rectangular is mostly found in areas where you have joints and fractures in sedimentary rocks. So they also form rectangles with respect to the different streams that are there. Different you know these can be mostly found in rocks which are easily jointed and fractured by chemical weathering that can happen due to the flow of running water on top of the surface. Then you have two kind of circular pattern of drainage basin. So first one is the annular. So if there is a dome that has been formed, and um, some kind of circular fracture patterns if there are surrounding that area, so you can have annular drainage pattern. Whereas radial usually is found either at if the elevated area is in the central part, or it can also happen that there is a basin and the water is moving towards the basin or away from the dome kind of a feature that is there. Okay, so mostly the radial pattern you can find in volcanic around volcanoes and domes that might have been created due to um, highly eroded in highly eroded areas. Also some structural domes would can be created in those regions. Now these are examples of some less commonly present drainage patterns. So you can have angular, subdendritic, centripetal, pinnate. So you can see all the different kind of drainage patterns. You have angular, so these streams are actually meeting the main channel at different angles. How in rectangular you had 90 degrees, angular they would be mostly angular, and they can range from 90 degrees to any other amount. So annular again, as you can see, around the dome that can be present. You have centripetal, so this in this area you can see that they are actually moving towards the central part, and being the water is being collected at the central part through the different streams. Then you have deranged, you have directional trellis, you have pinnate, then obviously dendritic we have already seen. You have radial trellis, you can see again kind of parallel kind of streams joining the main river. So these are, some of these are commonly found and some of these are not that commonly found on the earth. You can see that these are some of the real life examples as we see. So you can see the radial pattern over here. Okay, so these, the lines that we see are actually along the river channel. All the deposits that are present, that are forming along the channel, uh, actually can be seen from say satellite. These are sort of satellite imagery that we have. Okay, so you can see how this there is a radial kind of pattern that is followed by the different river, the stream channels. Then over here this is kind of a rectangular drainage pattern example. You can see the joints over here, you can see the joints over here and also here. So the river tries to flow through the joint. So this is again example of rectangular drainage. Over here you can see the trellis drainage pattern. So the erosion keeps happening in the parallel kind of a form, and this is the main river, that is the main river channel that is flowing, and more streams are kind of joining it in parallel fashion. Then over here you can see an example of parallel drainage. Okay, so these are these are parallel to each other, then these are parallel to each other. So this is an example of what we were talking about, the annular one. Okay, so there is no radial pattern as such, but the water is kind of flowing in a circular manner around a structural dome that is present here. So this is the Nilgiri hills, and the water is flowing around it in the annular drainage pattern. Then the most kind of very commonly found drainage pattern, that is the dendritic. So you can see how these kind of form like the branches of a tree. You can see, so they kind of spread out like how the veins in the tree leaves are present. So now as we saw how the different drainage patterns are formed, how they are a part of the different drainage basins. So each drainage basin for a matter has the potential to flood. So sometimes the floods are necessary to for the expansion of the flood plains, for the deposition of the fertile alluvium, okay, which supports most of our agricultural activities. So it is required, but when it causes a lot of harm to life and property, that are occurring around these drainage basins. So then it is necessary for us to understand how the floods are occurring, what is the frequency, and how we can try to mitigate it. So you can see for India, okay, so the flood prone areas are marked in blue, and most of these are actually situated along the areas where you have the major river systems of the India, and mostly the Indo-Gangetic plain area, and also the Indus the Indus drainage system, and also at areas where you have the deltas of the other rivers, like Krishna and Godavari. So this is like the deltaic region of that area. So this is kind of an very how the river channel or the river system would be interacting with the different elements of the human kind of settlements that we have. So this is the catchment areas. If you have sudden increase in rainfall or precipitation, so the discharge of the discharge carried by the river would increase, and then it would kind of flow over the land or the floodplain area around. Okay, and this would increase the say the amount of water that is being carried, and you can see that these kind of natural levees, if they are formed, they can help in kind of preventing the flood water to reach more area on the river banks. And it if these areas might be saved from the flooding, while this area where you have settlements between the two streams of the river that is flowing over here. So if there are no mitigating kind of structures over here, so this area would get flooded, and obviously the impact would be much greater. So the things that the factors that the floods depend on would be the size and nature of the river, vegetation in and around the river, the structures that are either built or either or naturally developed along the river channels. Okay, so levees, natural or artificial, and also the downstream water levels. So the flood intensity can be tracked by a plot called the storm hydrograph. So this actually gives us the understanding of how long it would take for peak discharge to occur after kind of the event that has given rise to the flood. It can be rainfall event, mostly if it is very sudden, and cloud burst could be one event which can also give rise to the flooding in that area. So there is a lag time between the peak of the event and the peak discharge. Okay, so this is called the lag time. Then after the rainfall event has happened, there is a rising limb. Okay, so there is this also depends on the lag time that is present between the peak rainfall and the peak discharge. And at a certain level, you have the bank full discharge. Okay, so that is the height at which the flood can occur. Okay, so if your peak discharge is below the bank full discharge, then flooding may not occur. Okay, but if it crosses the bank full discharge, so the probability of floods happening increases. And then after the peak discharge, there is a fall in the fall in the amount of discharge that is there, that is also called the falling or recessional limb. So anything this entire part, okay, so the blue shaded part is actually the storm runoff. So the storm runoff is mostly because of the rainfall event that has happened. Okay, so the rising limb can indicate how fast the water is reaching its peak discharge level, or how fast the uh, water is changing the water level of the channel. Okay, so if it is gentle in nature, that means the lag time is much more, and if the lag time is much more, most probably what would happen is that the peak discharge will not even reach the bank full discharge level. Okay, so uh, and if the, as we can see, if this is steeper in nature, so obviously the chances of floods increase in that zone. So flood intensity is actually the discharge along the channel over time, and it is influenced by the rate of runoff that is happening, the channel pattern, shape, and the number of tributaries and distance downstream. So this kind of helps us in understanding, high drainage uh, density and lower drainage density, how it can affect, and otherwise also how, vegetated area and non-vegetated area can also help. So flood intensity, if we see as varying with the basin shape and stream order. So you can see as per the drainage network of the river basin and the channel shape and the patterns um, can have an effect. So if there are more dendritic pattern, if it is present, so it would have a, it's this is more prone to flooding compared to this elongated drainage basin that we see. Okay, then the shape of the basin also has an effect, but as per the diagrams that we see here, it is not very significant. Okay, so it's not like the shape of the basin has a lot of control over the flood intensity that we see. The steepness of the profile does have a control. So if the drainage basin, or the area that is being flood, that we are trying to study the flood intensity of, is in an area which has steeper slopes, the chances of flooding in those areas are much higher than areas which have gentler slopes that are there. And then obviously drainage density, if the drainage density is it depends, it also you have to factor in the kind of geological setup that is present over there. Okay, as well as the shape and the number of stream orders. So if you have higher drainage density, then the time for the water, you know the, the peak discharge can be reached much faster than compared to drainage basin which has lower drainage density. Okay, so now since we know that flooding is very much possible in these areas which are surrounded by such river systems, so you need to have flood mitigation, uh, the protocol for flood mitigation has to be in place. At least like in places like India, where we are, most of the settlements are actually along and near, such large river systems that we have, and we keep hearing about instances where these floods are a very recurrent event that is happening. So we can have four different kind of flood hazard zones. Okay, so the zone 1, which is very much prone to flooding, would be the active floodplain areas. Then zone 2 is alluvial fans and plains. Okay, so these are usually the foothills, so with channels less than 1 meter deep. Okay, where the kind of the slope changes are actually happening. Then you have flood hazard zone 3. So these are upland and lowland slopes. The mostly the erosional and depositional processes are happening along the gradients. And the flood hazard zone 4 is usually where you have steep drainage, steep slopes, and the drainage basins that have very much erosive powers, that they cause incision, incised channels, and usually they occur in the mountainous regions. Okay, so you can see that most of the flood prone areas that we see over here are actually falling in the zone 1, like Uttar Pradesh, Bihar, West Bengal, Orissa. These are also, like, at least the coastal areas are prone to flooding also because of the frequent cyclonic events that are happening. But when we are talking about the flooding due to river basins is mostly concentrated in mostly the northern part of the area of India, and also coastal regions, because major river systems actually drain in these areas, and they form their deltas also in this region. So they are very much prone to flooding. So some mitigation methods that we can have is, you can have hard methods and soft methods. Yes. So these are required to stabilize the the river banks that are present, to avoid the water to flow over the banks and reach much lateral distances. So you can have creating more structures to hold the river banks in places. So you can reinforce the natural levees that are already present. You can also try to decrease the slope of the channel bed that is present, to prevent more erosion of the channel beds as well as the river banks. Then you can have soft methods. So these can be obviously increasing the vegetative cover along the river bank, so so erosion is lessened. And if the erosion is lessened, then the sediment deposits that are formed by natural flooding and flooding and receding of the water, they those structures would be more stable in nature, and it can contain the increase in discharge during any such flooding events. So obviously the kind of the very helpful man-made structure that we have are the building of dams. So they can help in controlling the increase in discharge by holding the water in the upstream region of the river, and allowing a controlled flow of the water in the downstream region. So they can help in controlling the floods that can wash away the downstream regions. So you can see obviously they also have environmental impacts, and a lot of environmental impacts can be seen in a downstream region where ecosystems are kind of uh, they are disturbed, and you have less sediment supply, nutrient supply, and fish yield also reduces. But kind of balanced out in the upstream region, you can have there are some issues that are siltation is one issue that we face in the upstream part of the dam. So while this is a very important and useful way to mitigate flood, we also have to try to mitigate the environmental impacts of building such dams. So sometimes kind of another natural hazard that can actually be caused is due to the obstruction in the uh, the sediment flow that is happening due to the building of the dam. Okay, so you can see that the debris flow is kind of one uh, this you can see is a kind of natural a type of a natural dam that can form, and it can obstruct the flow of the river. So but it can actually cause another if there's a lot of debris that are contained in one region, and with increase in the discharge, sudden increase in discharge, all this collected debris sediments can actually flow and obstruct the flow of the river in the downstream region also. So you can have complete blockage, partial blockage, and submerged dam blockage. So you can see the cross sectional area of these. Okay. So you have complete blockage, and then you have where the downstream region, there is not much kind of flow of the river. Now in the partial blockage, only one side, okay, so the head portion of the debris flow actually is where the water can pass through. And then you have which has submerged dam. So this debris flow is actually submerged below, and that it is still causing obstruction in the flow of the water. So this is kind of a a natural way that debris that are brought by the river can actually create dam structures. So this is all for today. So if there are any issues, any doubts that you have, please discuss it or put it up in the discussion forum. And the recorded lectures and the notes for this week's lecture would be put up in the NPTEL website. So you can go through them, and it will help you in understanding the lecture content that has already been put by the professor, as well as help you in uh, solving the assignments that are there. So thank you, and hope to see you in the next